All right, and good morning, everybody. I hope the voice is audible. Is my voice audible? Hello. Okay, I think I need to check it out by myself. All right, the voice is audible, and you're fine. Your connection is unstable. Uh-huh. So we are going to start. Yeah, is the screen visible? Yeah, I think the screen is visible. Mm-hmm. Yep, yesterday we completed recursion and arrays. Now we are supposed to read the stack. All right. Stacks, a fundamental data structure in computer science, are crucial for understanding algorithmic paradigms and solving complex computational problems. As candidates gear up for the GATE exam 2024, solid grasp of stack components is indispensable. These notes are designed to provide a concise yet comprehensive overview of stacks, covering key topics that are likely to be assessed in the GATE examination. A stack is a linear data structure in which the insertion of a new element and removal of an existing element takes place at the same end, representing as top of the stack. To implement the stack, it is required to maintain a pointer to the top of the stack, which is the last element to be inserted because we can access the elements only on the top of the stack. LIFO, last in first out in stack. This strategy states that the element that is inserted last will come out first. You can take a pile of plates kept on top of each other as a real life example. The plate which we put last is on top, and since we remove the plate that is at the top, we can say that the plate that was put last come out first. That is a great conclusion. Basic operations on stack. In order to make manipulations in stack, certain operations are provided to us. Push to insert an element into the stack. Pop to remove an element from the stack. Top returns the top element of the stack. Is empty returns true if the stack empty, else false. Size returns the size of the stack. Time complexity of stack operations. Okay, push and pop is empty and size returns of 1. Okay, the stack element needs to have size as well. It will. It is a trade-off between. It is a trade-off between time and space. Right? Implementation of stack using single linked list. To implement a stack using the single linked list concept, all the single linked list operations should be performed based on stack operations LIFO, last in first out, and with the help of that knowledge, we are going to implement a stack using single linked list. So we need to follow a simple rule in the implementation of a stack, which is last in first out, and all the operations can be performed with the help of a top variable. Let us learn how to perform pop, push, peek, and display operations in the following article. Initial tag having three elements and top have address 4. Yeah, this one, okay, 4880. First create a temp node and assign 44 into the data field and top in the link field, and in last assign temp into top. Okay. Pop all three elements, temp is equal to top is equal to top of link. Yeah, this is some terminology that I am unaware of. In the stack implementation, a stack contains a top pointer, which is the head of the stack, where pushing and popping items happen. It's the head of the stack. The first node. Okay, so this is like a linked list head. Makes sense, makes sense, makes sense. And the stack implementation, a stack contains a top pointer, which is head of the stack, where pushing and popping items happen at the head of the list. The first node has a null in the link field, and the second node link has the first node address in the link field, and so on. And the last node address is in the top pointer. Okay. Okay. This address is 4800. It is stored in top. 4900 is stored here. 5000 is stored here, and the last is none. Makes sense. The main advantage of using a linked list or arrays is that it is possible to implement a stack that can shrink or grow as much as needed. Using an array, we will put a restriction on the maximum capacity of the array, which can lead to stack overflow. Here, each node will be dynamically allocated, so overflow is not possible. Stack Overflow is a very famous website. Few people know about it. Push operation: initialize a node, update the value of the node by data. Now link this node to the top of the linked list and update top pointer to the current node. Pop operation: first check whether there is any node present in the linked list or not. If not, then return. Otherwise, make pointer, let's say temp, to the top of the node and move forward top node by one step. Now free this temp node. Peak operation: check if there is any node present or not. If not, then return. Otherwise, return the value of the top node of the linked list. Display operation: take a temp node and initialize it with top pointer. Now start traversing temp until it encounters null. Simultaneously print the value of the temp node. Exactly. You start the temp from here, you go all the way down until you encounter a null, and you print 44, 33, 22, and 11. That's it. Applications, advantages, and disadvantages. Okay, let's study. Application of stack data structure: function calls on recursion. When a function is called, the current state of the program is pushed onto the stack. When the function returns, the state is popped from the stack to resume the previous function's execution. Undo or redo operations. The undo or redo feature in various applications uses stack to keep track of previous actions. Each time an action is performed, it is pushed onto the stack. To undo the action, the top element of the stack is popped and the reverse operation is performed. Alright. Expression evaluation: stack data structure is used to evaluate expressions in infix, postfix, and prefix notations. Operators and operands are pushed onto the stack, and operations are performed based on stack's tab elements. Wait, operators and operands are pushed onto the stack, and operations. I don't think that's true. Both operator. I think only operators are pushed, right? Sometimes only operators are pushed. Okay. Okay. Operands are not pushed. They go directly. Yeah. Okay. We did not study prefix. That's why we got that out. Browser history. Web browsers use tags to keep track of the web pages you visit. Each time you visit a new page, the URL is pushed onto the stack, and when you hit the back button, the previous URL is popped from the stack. Balanced parenthesis: stack data structure is used to check if parentheses are balanced or not, and operate. An opening parenthesis is pushed onto the stack, and closing parenthesis is popped from the stack. If the stack is empty at the end of the expression, the parentheses are balanced. Yep. Backtracking algorithm. The backtracking algorithm uses stacks to keep track of the state of the problem-solving process. The current state is pushed onto the stack, and when the algorithm backtracks, the previous step is popped from the stack. Yes, backtracking. Recursive backtracking is one of the famous techniques. Easy implementation. Stack data structure is easy to implement using arrays or linked lists, and its operations are simple to understand and implement. Uh-huh. Yes, you can either use arrays or linked lists. Efficient memory utilization. Stack uses a contiguous block of memory, making it more efficient in memory utilization as compared to other data structures. Okay. But if you implement it well in list, I don't think this statement is true. We are having a lot of doubts. Wait. Yeah, we already had it. Okay, it opens only one tab at a time. But if you use yep, we are correct here. So it needs to kind of say like array-based implementation of stacks. Fast access time. Stack data structure provides fast access time for adding and removing elements as the elements are added and removed from the top of the stack. Helps in function calls. Stack data structure is used to store function calls and their states, which helps in the efficient implementation of recursive function calls. Supports backtracking. Stack data structure supports backtracking algorithms, which are used in problem solving to explore all possible solutions by storing the previous states. Used in compiler design. Stack data structure is used in compiler design for parsing and syntax analysis of programming languages. Enables undo or redo operations. Stack data structure is used to enable undo and redo operations in various applications like text editors, graphic design tools, and software development environments. Okay. Disadvantages of stack. Limited capacity. Stack data structure has a limited capacity as it can only hold a fixed number of elements. If the stack becomes full, adding new elements may result in stack overflow, resulting in loss of stack. He kind of copy pasted it. And again, this is only true for our implementation. And again, this is only true for our implementation. For Ellen, there is no stack overflow unless you don't have RAM size. No random access. Stack data structure does not allow for random access to its elements, and it only allows for adding and removing elements from the top of the stack. To access the element in the middle of the stack, all the elements must be removed. That is true. Memory management. The stack data structure uses where is this? Stack data structure uses a contiguous block of memory, which can result in memory fragmentation if the elements are added and removed frequently. Some are not suitable for certain applications. Stack data structure is not suitable for applications that require accessing elements in the middle of the stack, like switching or sorting algorithms. Stack overflow and underflow. Stack data structure can result in stack overflow if too many elements are pushed onto the stack, and can result in stack overflow if too many elements are popped from the stack. Recursive function call limitations. While stack data structure supports recursive function calls, too many recursive function calls can lead to stack overflow, resulting in termination of the program. That is true. In fixed to postfix operation in stack to convert infix expression to postfix expression, we use the stack data structure, scan the infix expression from left to right. When we get an operand, add it to the postfix expression, and if we get an operator or parenthesis, add it to the stack by maintaining their precedence. Uh-huh. Certification by IBM. Yeah, let it be. I don't. I just need a AI course. Complete data science. Alright, below are the steps to implement the above idea. Scan the infix expression from left to right. If the scanned character is an operand, put it into the postfix expression, otherwise do the following. If the precedence and associativity of the scan operator are greater than the precedence and associativity of the operator in the stack, or the stack is empty, or the stack contains left parentheses, then push it in the stack. Okay, power exponent operator is right associative and other operands are left associative. Okay, I have no idea. Check especially for a condition when the operator at the top of the stack and the scan operator both are the condition. Okay, there is like some exception for this operator because it is saying it is right associative, but I don't think all of the depth is necessary at this point. In all other cases, when the top of the operator stack is the same as scan operator, then pop the operator from the stack because of left associativity due to which the scan operator has less precedence. As pop all the operators from the stack with a greater or equal to in precedence than that of the scan operator after doing that push the scan operator of the stack. Okay. Um, that that might be professional. If operand ultra compressed memory trick. Operator pop stronger ones. Uh, okay, this is exactly opposite. The plus needs to be at the bottom. Right. Okay, that makes sense. To evaluate a postfix expression, we can use a stack. Iterate the expression from left to right and keep on storing the operands onto a stack. Once an operator is received, pop the topmost elements, evaluate them, and push the result into the stack again. Fine. Okay, he is writing evaluation. I was thinking in infix. Alright. This is only infix to postfix, not prefix. Right? Towers of Hanoi using stack. Okay, okay. Yep, we are at the end almost. Towers of Hanoi is a mathematical puzzle where we have three rods A, B, C, and then disks. Initially, all the disks are stacked in decreasing value of diameter. Here, the smallest disk is placed on the top, and they are on rod A. Okay, decreasing. The objective of the puzzle is to move the entire stack to the other rod. Here, consider C. Obeying the following simple rules, only one disk can be moved at a time. Each move consists of taking the upper disk of one of the stacks and placing them to the top of another stack, i.e., a disk can be moved if it is the uppermost disk of a stack. No disk may be placed on top of a smaller disk. The idea is to use helper node to reach the destination using recursion. Shift n minus 1 disks from A to B using C. Shift the last disk from A to C. Shift n minus 1 disks from B to C using A. Uh-huh. Okay, that makes sense. That makes sense. So first we are shifting the n minus 1 disks to B using C. So it will be placed here, here, and here. Okay, and this is placed here, just like this. And now we need to use B A as the helper node. It will go here, and it will go here, and it will go here. Right. I cannot code it. The time complexity is about to burn. There are two possibilities for it. Uh-huh. Fibonacci numbers, alright. Yep, this is in the dark mode, it is not visible. So, what is this? 9 is 34 is saying 0, you will start with 0, 0 plus 1 plus 1 plus 2, 1 plus 1 is 2. Oh wait, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. Wow, 5 plus 8 is 13, 8 plus 13. Huh? Okay, okay, that is messed up. 0 plus 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13. How many terms are there? 1, 2, 3, 4, 5, 6, 7, and 8. Okay, you need the ninth term. Okay. How did I get that for Fibonacci? Alright. Yep, 13 plus 21 is 34. Yeah, it is. So, how is it the ninth term? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It is not the ninth term if you consider 0. Cannot this? Okay, a little bit. Alright, so the index is starting from 0 for them. That's why when counting, the ninth term is actually the 10th term. We completed stacks, people, and We have queues, linked list, trees, heaps, and graphs, and hashing to complete the data structures. Right, I need to eat some tiffin. Guess we need to have a break timer. Mm. So can you, yes, can you do this? Yeah. Alright then, I will be back in 10 minutes. We are back. Yeah, my voice is audible, right? Yep, this clock is actually being a good thing. Let's add another timer. How to add another? Okay, here. How many shall we do? 50 to 10, right? Okay, this is the only way. Yeah, 50 to 10, or maybe. Now we will do 50. Let's see how that thing works out. You need to change the notification. Okay, works out. Yeah, so we are studying queues now. Queue is defined as a linear data structure that is open at both ends and the operations are performed in the first in, first out order. Queue is a list which all additions to the list are made to one end and all deletions from the list are made to another end. The element which is first pushed into the order, the operation is first performed on that, alright? So dequeuing from the front and unqueuing from the last, as simple as that. To implement a queue using an array, to create an array of size n and take two variables front and rear, both of which will be initialized to 0, which means the queue is currently empty. Okay. Rear is the index up to which the elements are stored in the array, and front is the index of the first element of the array. Okay. So this is front for dequeuing and rear for unqueuing. Now some of the implementations of the queue operations are as follows. Unqueue, addition of an element to the queue, adding an element will be performed after checking whether the queue is full or not. If rear is less than n, which indicates that the array is not full, then store the element array of rear and increment rear by 1. But if rear is equals to n, it is said to be an overflow condition as the array is full. And queue has a of one-time complexity because you are just pushing into the queue, alright? DQ, removal of an element from the queue. An element can only be deleted when there is at least an element to delete if rate is greater than 0. Now the element at array front can be deleted, but all the remaining elements have to shift to the left by one position in order for the DQ operation to delete the second element from the left on another DQ operation. DQ has O of n time complexity. Yeah, this is what I have been thinking. Does wait DQ operation queues using arrays O n time complexity. It depends on how the queue is implemented using an array. Alright. If you DQ, you should have to left. Yes, in naive version, okay. Proper array queue. Yeah, you can increment pointers of front and let's say the same as the queue is full and you and queue for elements for then number into the nodes and the location and you cannot. Wow. Okay. We have studied circular queues, but I was not able to connect the normal queues and circular queues. Mhm. Nice. Nice. So this is a naive queue. That's what they have been saying. Front get the front element from the queue. The array is not empty. Accessing the front element has often time complexity. I'm about to sneeze. Oh god. That is the worst feeling, when you wanted to sneeze but the sneeze won't come out. Anyways, display print all the elements of the queue. If the queue is not empty, traverse and print all the elements from index front to rear. Displaying all the elements is often time complexity or space complexity is often alright. Implementing queues using linked list. To implement a queue using linked list, maintain two pointers, front and rear. The front points to the first item of the queue and the rear points to the last item. Okay. And queue. This operation adds a new node after the rear moves the rear to the next node. Right. DQ. This operation removes the front node and moves the front to the next node. Okay, rear to the next and front to the next. Alright. Now some of the implementations of queue operations are as follows. Create a class queue node with data members, integer data and queue node. Next pointer to the next node. Since this guy is talking classes, maybe he is implementing it in C++ because you cannot create classes in C. Create a class queue with data members, queue node and rear. Okay, create a class queue with the data members, queue node front and rear and queue operation with parameter x. This is the algorithm. Alright, if I'm not wrong. This description is most likely C++. References. Reverse engineering the language and design from coding. ChatGPT really gives you a motivational boost. Mhm. A queue can be implemented using two stacks. Okay. Yo, this is a question that I have seen in Git. That queue to be implemented be queue and stack is implement queue. Okay, do we need this engineering? Okay, we got a priority queue. The extras double-ended queue. Okay, deck, yeah, deck. Gate archives. Okay, let's read it. What will happen? A queue can be implemented using two stacks. Let queue to be implemented be queue and stacks use it to implement queue be stack 1 and stack 2. Queue can be implemented in three ways by making an queue operation costly. This method makes sure that the oldest entered element is always at the top of stack 1, so the dequeue operation just pops from stack 1. To put the element at top of the stack, stack 2 is used. While stack 1 is not empty, push everything from stack 1 to stack 2. Push x to stack 1, assuming size of stacks is unlimited. Push everything back to stack 1. Okay. Wait. This seems good engineering, but I have not encountered this in academics. Shall we discuss this our style? When the rules of structure is thinking. KO is FIFO, stack is LIFO. They are opposites, so the real question engineers asked was, can we reverse LIFO behavior twice to simulate FIFO? And the answer was yes. Always keep stack one in correct queue order. Oldest element must be on top, so DQ becomes easy. Just pop it. Bottom is oldest. Because how transfers happen, stack one is arranged so that oldest element, that's why DQ is easy. Mhm. Let's stack one correct elements normally, only reverse when necessary. Alright, alt stack 2. Amortized time. Right, so. Okay, I thought of asking something. I forgot what it is. Yeah, I understood it. No worries. Okay. Did we get any chats? No, we did not. Okay. Circular queue is an extended version of a normal queue where the last element of the queue is connected to the first element of the queue, forming a circle. The operations are formed based on FIFO principle. It is also called ring buffer because it is of shape of a ring and it is acting as a buffer. Quite simple to understand. Operations on circular queue front get the front element of the queue accessing the front element has a and time complexity. Yeah, I thought of asking what is amortized analysis. Yep, now I remember. Like how did O n wait O n become O n? Mhm. So amortized analysis means average cost per operation over a sequence of operations, not worst case of a single operation. If I perform many operations, what is the real average cost per operation? Okay, okay. Yep, looks expensive. Okay, Nice. Yes, we kind of mapped out two important concepts together, and that's good. That's good. Where did we read that amortize analysis? Okay, ChatGPT gave that. All right, applications of circular queues. Yeah, we are reading this right, and Q value. This function is used to insert an element into the circular queue. In a circular queue, the new element is always inserted at the rear position. Check whether the queue is full, that is, rear end is in just before the front end in a circular manner. Okay. If it is full, then display queue is full, else insert an element at the end of the queue. Uh, okay. Yeah, because printer queues. Just because you assign a new printer job, the oldest printer job does not get terminated. Nice. All of this desired behavior. System philosophy. Mhm. Okay, at least I'm thinking, and I am happy for that. Check whether the queue is full. That is, the rear end is in just before. Alright. This function is used to delete an element from the circular queue. In a circular queue, the element is always deleted from the front position. Yes, check whether the queue is empty. If it is empty, then display queue is empty. Let's get the last element and remove it from the queue. The time complex head is often Application to circular queue in a page replacement algorithm, a circular list of pages is maintained, and when a page needs to be replaced, the page in the front of the queue will be chosen. The page in the front of the queue will be chosen, alright. Page replacement algorithm. We'll study that in OS. Computer systems supply a holding area for maintaining communication between two processes or two programs. This memory is also known as ring buffer. Did he write it over there? Okay, yeah, he wrote it over there. CPU scheduling. In the round robin scheduling algorithm, a circular queue is utilized to maintain the processes that are in the ready state. Alright. A priority queue is a type of queue that arranges elements based on their priority values. Examples with higher priority values are typically retrieved before elements with lower priority values. If we add an element with high priority value to a priority queue, it may be inserted near the front of the queue with an element, while an element with a low priority value may be inserted near the back. Okay, because it needs to get popped out, like dequeued out quickly. That's why it is near the front, an element with the higher priority. Types of priority queues, descending order priority queue. Okay, descending order priority queue or max heap. Higher priority values are given more priority as compared to lower priority values. Yes, that is max heap. Ascending order priority queue or min heap. Lower priority values are given more priority as compared to higher priority values. See, in the advanced data structures, they use it to say priority queues or use it to implement heaps, but I did not know. But now things are a little bit clear. Properties of priority queue. Every item has a priority associated with it. An element with high priority is dequeued before an element with low priority. Mhm. If two elements have the same priority, they are served according to their order in the queue. If in the below priority queue, an element with maximum ASCII value will have the highest priority. Alright. Maximum ASCII value. Okay, okay. Maximum ASCII value is O. Alright. Okay, he is highlighting it. Yep, yeah, yeah. Makes sense. Makes sense. Operations on priority queue. Insertion in a priority queue. When a new element is inserted in a priority queue, it is placed after the last element and is swapped with the parent node. If the order is incorrect, the swapping process continues until the elements are placed in the correct order. Okay, this is heap. Basically a heap. Deletion in a priority queue. 1 hour 7 minutes of stream, alright. It will remove the element which has maximum priority first. This removal creates an empty slot which will be further filled with new insertion. Then it compares the newly inserted element with all the elements inside the queue to maintain the heap invariant. Heap invariant, alright. Okay, that makes sense why we are using trees. Now that makes sense why we use a tree data structure to implement a priority queue. If it were linear, then the time will be linear. If it were a linear data structure like a queue, it will be linear time complexity. So we used tree for logarithmic time. Alright. Peak in a priority queue. This element helps to return the maximum element from max heap or the minimum element from min heap without deleting a node from the priority queue. The time complexity is O of 1. Applications of priority queue digits through shortest path algorithm using priority queue. There are links for them too if we wanted to practice. When the graph is stored in the form of adjacency list or matrix, priority queue can be used to extract minimum efficiently when implementing Dijkstra's algorithm. Okay. Prim's algorithm. It is used to implement Prim's algorithm to store keys of nodes and extract minimum key node at every step. The priority queue, also known as the fringe, is used to keep track of unexplored routes. The one with a lower bound on the total path length is smallest is given highest priority. The one for which a lower bound on the total path length is smallest is given highest priority. Alright, we are just exploring like shortest path algorithm. Heap sort is typically implemented using heap, which is an implementation of priority queue. Operating systems. It is also used in operating systems for load balancing, interrupt handling. So yeah, balancing because we are using balanced backtrace history in some way or the other. Double-ended queue decker is a generalized version of queue data structure that allows insert and delete at both ends. Front get the front element from the deck. Accessing the front element has O of one time complexity. Rear get the last element from the deck. Accessing the rear element has O of one time complexity. Push front inserts the element X at the beginning of the deck. Inserts the element X at the beginning of the deck. Okay. Insert an element at the back of the deck. Yes. Okay. Okay. Yeah, it is basically you can push from front and back, and you can also pop from front and back. That is it. And you can also view the front element and the rear element. Very simple philosophy. Applications of double-ended queue used in job scheduling algorithms. Job scheduling. Okay. Uh, JSSP, right? Job shop scheduling something. Yeah, I guess I heard it in algorithm greedy or something. In a web browser, history recently visited URLs are added to the front of the deck and the URL at the back of the deck is removed after some specified number of operations of insertions at the front. Okay. Yeah, because you cannot store everything. Then it will be some memory overhead or maybe overflow of memory. Storing a software's application list of one-to-one read operations, alright. In caching systems to cache frequently accessed data. Okay, DEX can also be used to store cache data and efficiently support operations such as adding or removing data from both ends of the deck. Yeah, I am not going to touch the archives right now. No, I'm not going to touch the archives. And yes, this is a good article. This is a good article. Okay, we got linked lists. Now we got linked list. I guess we will complete this article and take a break. The linked list notes for GATE exam is a comprehensive resource designed to aid students in preparing for graduate aptitude test in engineering. Focus specifically on linked list of fundamental data structure and computer science. These notes offer a detailed and structured approach to mastering the subject within the context of the GATE examination. Okay. See, what an ironic thing. We studied stacks and queues and now we came back to linked lists. Alright, but we have studied most of the things, it's alright. A linked list is a linear data structure in which the elements are not stored at contiguous memory locations. Okay. Unlike an array, a linked list consists of nodes where each node contains a data field and a reference linked to the next node of the list. The elements in a linked list are linked using pointers. Singly linked list. A single linked list is a linear data structure in which the elements are not stored in contiguous memory locations, and each element is connected to only to its next element using a pointer. This is the basic implementation of a linked list. The elements in a linked list are linked using pointers to the next node. Operations on singly linked list. Insertion at the beginning of the linked list. To insert a node at the beginning of the linked list, we change the next pointer of the new node to the current head and make the new node as the current head. Yeah, insertion at the beginning. Basically, what you do is you put a node here and you make this connection and you update the head from this to this. That is it. It takes over one time. That's it. Insertion at the end or after a given node. To insert a node after a given node, we need to update the next pointer of the new node to the next pointer of the given node and update the next pointer of the given node to the new node. Time complexity of n, as in worst case we may traverse through all the nodes of the linked list. Actually, it is guaranteed of n. I have understood it. Technically speaking, it is guaranteed on, right? No, it is not guaranteed. Okay, yeah, obviously. No, what I try to say is a case in which you need to insert at the end of the linked list, not middle, not start, and no pointer to last. Yes, in that design it is guaranteed often. Okay, we have understood it. Yeah, we did not put the constraints proper. That's it. And where are we? Searching an element, we can search a node by traversing through the linked list and comparing the nodes one by one. Yeah, O of n at maximum. Find length of the linked list. We can find the length of the linked list by traversing through the linked list and maintaining the count of nodes. It is also guaranteed O of n. If I'm not wrong, reverse a linked list. We can reverse a linked list using three pointers, current, previous, and next to keep track of nodes to update reverse lists. Deletion at the beginning of the linked list. To delete a node from the beginning of the linked list, we change the head to the next of the current head and delete the previous head. Deletion at the end or after a given node. To delete a node after a given node, we need to update the next pointer of the given node to point to the node which is present after the node to be deleted. Yeah, kind of like skipping a node. Time complexity. So when as a worst case we may traverse through all the nodes in the linked list. If a pointer is given, if a pointer to the node to be deleted, then also it is open. If the pointer to the previous node of the node that is to be deleted is given, then it is O of one. Wow, we came up with an excellent conclusion here. I need to tell it to ChatGPT. If the pointer to the node to be deleted is given, then also it is on because we need the brief pointer and can't get directly from single increment. But if the pointer to the previous node of the node to be deleted is given, then the time complexity is 1 because we can get the current and next from grave. Is that a valid way to think about it? You copy data from the next node and delete. Oh wow. Okay. CF is overkill. Alright. Hmm. Double linked list is a special type of linked list in which each node contains a pointer to the previous node as well as next node of the linked list. Okay, okay. That is it. No, that is really it. Alright. Okay, it is high time that I take a break in like 2 minutes. Double linked list is a special type of linked list in which each node contains a pointer to the previous node as well as the next node of the linked list. The elements in a linked list are linked using pointers to the next node as well as to the previous node. Alright. All operations of double linked list are same as single linked list except we need to update the previous pointers along with the next pointers whenever we insert or delete a node. Circular linked list. The circular linked list. Awesome. A circular linked list is a linked list where all nodes are connected to form a circle. In a circular linked list, the first node and the last node are connected to each other, which forms a circle. There is no null at the end. The elements in the linked list are linked using pointers to the next node, with the last node pointing to the head of the linked list as shown. Alright, makes sense. There are two types of circular linked list: circular single linked list and a circular single linked list. The last node of the list contains a pointer to the first node of the list. We travelers, alright, people. Someone's calling me, and I gotta go. And bye. I will stream again after some time.